For this section, linear approximations and differentials, we're gonna study what we have learned before about derivatives, and we're gonna apply it to approximate the value of some functions for whenever it is impossible for us to just simply evaluate. So that's the usefulness for linear approximations. And then in differentials, we can approximate functions to simpler functions so that different calculations can be a lot more simplified. So in general, I'm going to have a function for which I know I can find the derivative of. So this function is going to be differentiable at some particular point, let's say at x equals a. And I know that I have a tangent line here for which I can find the slope. So that would be f prime of a. So this function, if I zoom in on the calculator a lot of times, this function, from whatever it may come from, sine of x or anything crazy like those rational functions, ultimately it's going to start behaving like a line. So in that sense, locally or around x equals a, it almost looks like a straight line. So this function and the tangent line to that point are going to start looking almost the same. It will never be the same, but it almost looks the same. And that is true for any x on the domain. Although you know that the tangent line changes as the value of a changes. Like if I'm doing it for another value of x, let's say b, for b the point will be over here and the tangent line will be totally different. But even for this tangent line, locally around this point with x coordinate equal to b, the tangent line and the function itself will be very similar, only for values around b. So for around a, only for values around x equals a, the function and the tangent line have almost the same y value. So that's the usefulness of this part. So we see here that this is the equation of a tangent line. And then for whenever x is close to a, we have f of that value is almost the same as the y value from my tangent line. So for example, I have this equation, I have this function, you know, it's a square root and it's been moved left 3 times. So around x equals 1, we're going to be able to approximate what are the values of these 2 square roots. So let's see how this works. I always like to work with graphs so that I can make sense of what's happening. So I have my function that has shifted 3 units to the left, and then remember the pattern for the square root. Square root of 1 is 1, and the square root of 4 is 2, and then the square root of 9 is 3. So I know very accurately that my function goes like this, and this is the graph of y equals the square root of x plus 3. Sorry. So they are asking me at a equals 1. So at a equals 1, I'm looking at this point. Okay, so it says use this fact and use this value of a to approximate the numbers square root of 3.98 and square root of 4.05. So the first thing I have to do is take my function and find the derivative. So f prime of x, remember taking derivatives of square roots, just write it as a power and then apply the power rule. So this would be 1/2 x plus 3 to the negative 1/2. And if there was something inside, then it would be times the derivative of the inside, but the derivative of the inside would be 1, so I'm just going to leave it like that. And then I'm going to find what is f prime of my value of interest, which is 1. So f prime of 1, that just makes me evaluate at 1. And then 1/2 4 to the negative 1/2. Remember that the negative makes a reciprocal, so this is square root of 4, and that will be 1/4. So that means the tangent line has a slope 1/4. So how do I write the equation for the tangent line? This is something that surprisingly very simple, and not a lot of people could do well on exam 1. So let's see how it works. I can find the point slope form of this tangent line, which will be y minus y1 equals the slope x minus x1. I know the slope is 1/4. I'm gonna use this point, which is the point 1, 2. So x minus 1 and y minus 2. Now I'm gonna just write it as y equals mx plus b. So it will be 1/4 distribute minus 1/4, and then this minus 2 comes here as plus 2. Now I'm just gonna simplify, and I have 1/4 of x plus this will be 8/4 minus 1/4 will be 7/4. So now I have my equation on slope-intercept form, and this is the equation of the tangent line. Now I know that to approximate this y value, I'm gonna call that my linearization. So my linearization is saying linearization of x is let's see, f of a plus f prime of a x minus a. This is linearization of f at a. So in this case, for this example, it will be linearization of f at 1, which just means what is the approximate y value for my function at a equals 1. So f of a is 2, plus f prime of a, f prime of 1 is 1/4, times x minus 1. So as you can see, this will turn out to be, when I distribute, it will turn out to be my tangent line equation, which is just to show you that if you were able to find the tangent line equation, you're able to find the linearization of f of a, and that is not a problem. It's just something that has a different name. So how do I use that to find the square root of 3.98 and the square root of 4.05? So this is the way you have to think about in here. X is not 3.98. This is the result that you're trying to figure out by using this function. And remember that the x's that you are dealing with need to be around 1. So how much is this x that you can use to calculate this? Well, if you compare these two functions, I see that the square root is the same and the inside looks different. So if 3.98 is x plus 3, how much is the value of that x that I need to use? So if 3.98 is x plus 3, therefore x is 0.98. So that's the x that happens to be around 1 that I can use the tangent line for as an approximation of the real y. So a square root of 3.98 is about, well, it's exactly square root of x plus 3 when x is exactly 0.98, but it's about 7/4 plus, remember that our equation was 1/4 of that x. So when you do that out, you get 1.995, which is pretty cool because you have made an approximation of a square root that without a calculator you weren't able to do that. You can, I mean, manually it's a very hard problem to do. I mean, it's worse than long division. So this is something that can be done manually without a calculator in case if the world ends or something like that, that you can approximate. So this is a number near 4, so the square root of 4 is 2. Square root of 3.98 logically is going to be a number around 2. And then use it for taking the square root of 4.05. So the same idea, how much is x if x plus 3 is 4.05? So 4.05 is x plus 3. So minusing 3 both sides, x is 1.05, which is a number near 1. So the square root of 4.05 is about, again, 7/4 plus a fourth of that x, 1.05, and that is about 2.0125. So the square root of 4.05 is about around 2 as well. Now, are those estimates really close to the real value? And I would say yes. I mean, you can take the calculator and find how much those are. Not exactly, because the calculator offers an approximation as well. These are irrational numbers. However, these decimals are very close to the decimals that you will have if you have a calculator. Now, are they overestimates or underestimates? This is the values that I get from the tangent line. So from the tangent line, I will get this y value, and the real one will be here. So you see how the y value for the real thing is lower than the y value from my tangent line. So in this case, this is an overestimate because I'm saying a y value that is higher than the real thing. And then for this 0.4, I'm sorry, that was for this one. For the other one, it's the same. The y value, the real y value, is below the tangent line. And you can generalize that as if the tangent line is above the graph, then you're gonna be overestimating. And if I have, for example, a function that looks like this and the tangent line is over here, then the tangent line will be underestimating the real y value. The real y value is here, and on the tangent line will be over here. So overestimating if the tangent line is above the graph around that point. Now on the slides you have several values for the real function, the actual value, and from the linearization at 1. So you can see how whenever x was close to 1, these values and these values are pretty much good enough, very close to each other. But as you go away from 1, let's say 2 is too far. You see you have 2.25 and here you have 2.236. If you were talking about averages, then you know that this is way far, because averages, if we're talking about the US population and you happen to have 2.25 children per family in average, or 2.23 children per family, then this will add, for every 100 people, this will add 2 extra kids. So imagine how many hundreds of people live in the US, and you will be overestimating the population by a lot. So you know, for x equals 2 or 3, definitely the approximation, it is not as approximate as it would claim to be, and that is just because the tangent line changes for every value of x. So when x is 2 and 3, we're going to have a different tangent line with a different approximation near those values.